Okay, so our first example regarding the radial and transverse inertial reference frame reads: the smooth 2 kg cylinder has a pin P through its center, which passes through the slot in arm OA. If the arm is forced to rotate in the vertical plane at a constant rate of 0.5 radian per second, determine the force that the arm exerts on the peg at the instant that the angle is equals to 60 degrees. So, as usual, let's first write out all the necessary givens. So, one of the givens is, of course, the mass of the cylinder C, and that is equals to 2 kg. The speed, gravitational speed, which is 0.5 radian per second, and the angle is at 60 degrees. Of course, any other given are shown on the space diagram. So what is required of us? The required is the force. Determine the force that the arm OA exerts on the peg or on the cylinder C. That is the force. So as part of the solution, let's draw the free body diagram. So first things first, let's establish the axis for radial and transverse. So we have here, this is the positive radial transverse, and this is the positive radial direction. So for our free body diagram, this is the weight, and of course, since there is a surface that acts on the cylinder C, we have a normal force, and let's label that N sub G, the normal force exerted by the ground. Okay, so any other force that acts on the cylinder C? Of course, there is another body, and that is the arm OA. So let's assume the direction for that in this direction. Let's say that one. So let's still call it normal force by the arm or normal force P. Okay, because if we're going to magnify that one here, you can see that this is the peg and this is the arm. This is the outer part of the cylinder. This is the ground. So the ground exerts force, normal force, on the cylinder C, and since there is a contact also between the arm OA and this part of the cylinder, then there must also be a normal force, and that is exerted by the arm on the point P. Okay, so that's the reason that there is that force NP. So let me erase this one. Okay, so are there any other forces that act on the cylinder C? We have the weight, we have the normal force by the ground, and the normal force by the arm OA. So I guess there are no other forces, and we're now ready to formulate the equations of motion along the radial and transverse axis. Okay, so first we have the sum of forces along the R is equals to MAR. Let's what are the forces along the R? Since this is the angle, this is also the angle theta, and this is also the angle theta. The same with this. Okay, so this is the positive direction of the positive r, and this is the direction of the positive theta. So that would be w sine theta minus ng still sine theta is equals to mar. Of course, that would be mg sine theta minus ng sine theta is equals to mar. Okay, so for the summation of forces along the transverse, it would be this is the positive sense. So we have w cosine theta and plus np minus ng, it would be cosine theta equals to m a theta. So finally we have mg cosine theta plus np minus ng cosine theta is equals to ma theta. So this is our equation number 1, this is equation number 2. Okay, so let's identify what are the unknowns. For equation number 1, the unknown is ng and ar. For equation number 2, we have np and a theta, since ng will be known if for equation number 1. So let's find out first the value of radial acceleration and the transverse acceleration using kinematic analysis. Okay, so first we have course theta, and that is 60 degrees. Theta dot, we have a 0.5, and of course theta double dot is 0 because derivative of constant is 0. So for the radial distance, let's get that by trigonometric relation. Let's relate the 0.4 meter to the angle theta and the radial distance. So that would be sine theta is equals to 0.4 over r. 4 over r. Okay, as you can see here, sine theta is equals to 0.4 over r. And that would be r equals to 0.4 over sine theta. Okay, r 0.4 sine theta. Or 0.4 second theta. So that is the expression for r in terms of theta. Now we can solve for r dot and r double dot by deriving the function. So first for r dot, we have a 0.4, and derivative of cosine theta is equals to negative cosecant theta cotangent theta, and the derivative of the angle itself, which is theta dot. Okay, so we have three variables. We have cosecant theta, cotangent theta, and the rotation, the angular speed. So since that is constant, you can just simplify the equation. That will be 0.5 times 0.4 is negative 0.2 cosecant theta cotangent theta. And last, for the r double dot, we need that one. Let's derive again. Negative 0.2. Derivative of cosecant is still negative cosecant theta. Yes, cotangent theta and theta dot, and times the right part, which is the cotangent theta, plus derivative of the right part, which is cotangent, and that would be cosecant squared negative cosecant squared. That is the derivative of cotangent theta times the derivative of the variable, which is theta dot, and times the left part, which is the cosecant theta. Okay, so let's simplify. We have a theta, we have cosecant also, and cosecant here. So we can extract that out. Let be negative cosecant theta, dot, negative cosecant theta, dot. Okay, so negative 0.2 times negative cosecant theta, then theta dot. So what remains is cotangent theta. Oh, I forgot to include theta dot here. Theta. That would be cotangent squared theta plus cosecant squared theta. Okay, so by simplifying, we have 0.2 times 0.5. That would be plus 0.1 cosecant theta times cotangent squared and cosecant squared. Okay, so now we have equation for r dot and r double dot. So we can now solve for AR and A theta. So the formula for AR is equal to r double dot minus r theta squared, and for A theta that would be r theta double dot plus 2 r dot theta dot. Okay, so let's plug in the values. R double dot at angle of 60 degrees, this would be equal to r is equals to 0.192. 0.192, that would be, the unit is equals to meter per second squared. Meter per second squared. And for the r dot, that is equals to negative 0.133. Negative 0.133 meter per second. And of course, the r is equals to 0.461. 0.462 meters. Okay, so plugging the values, AR would result to r double dot is 0.192 minus 0.462 times 0.5 squared. That is equals to 0.0770 meter per second squared. So for A theta, that would be 0.462 times 0 plus 2 times r dot, which is negative 0.133 times theta, which is 0.5, and that would be negative 0.133. Okay, so we now have AR and A theta. We can now solve for NG and NP. Okay, so let's plug in the values. M is equals to 2 kilogram. 2 kilogram times the gravity, which is 9.8 meter per second squared, sine 60 degrees, minus normal force exerted by the ground times sine 60 degrees is equals to 2 kilogram times the acceleration of AR, 0.0770 meter per second squared. Okay, so solving for NG is equals to 19.4 Newton. Okay, so this is one of the forces that act on the cylinder C. Here, let's continue, and that would be 2 kilogram multiplied by the gravity cosine 60 degrees plus NP minus of course the NG, which is 19.4 Newton, times the cosine of the 60 degrees is equals to 2 kilogram times the A theta, which is negative 0.133 meter per second squared. So the resulting value of that NP is equals to negative 0.356 Newton. So we have two forces, NG and NP. NG is the normal force that is exerted by the ground against the cylinder C, and that is the outer surface, while NP is the normal force still, but this is the normal force that comes from the arm OA against the peg, which is the center part of the cylinder. So the value of NG is positive 19.4. It means that the original assumption of the direction of the NG is correct, meaning it goes in this direction, it goes upward. But the value for NP is negative 0.356, which means that the assumption for the direction of NP is in fact opposite. It means that the NP is in this direction. Okay, and that is the correct free body diagram. And since the question is the force that the arm exerts on the peg at the instant the angle is 60 degrees, then the only true answer or the only required force is that of NP. Okay, so that is the only force exerted by the arm against the peg at 60 degrees, and that is 0.356 Newton.